Imagine a high-speed vehicle traveling in reverse. It slams on its brakes and violently slows down. In physics, this vehicle just experienced positive acceleration. Tracked on a number line, velocity changes from -8 to -5. Since -5 is greater, velocity increased, making acceleration positive. But speed, the absolute value of velocity, drops from 8 to 5, shrinking toward 0. The cognitive trap here is a reliance on everyday language. We are conditioned to assume that positive acceleration automatically equates to an object going faster. To accurately map motion, we must separate our physical intuition of speed from the strict mathematical signs of derivatives. This diagram outlines a 1D kinematic framework. We define position, denoted as s, strictly as where an object is relative to an arbitrarily chosen 0 point and a chosen positive direction. The mathematical sign of s does not imply any movement. It merely dictates which side of the 0 point the object currently occupies. Velocity is the rate position changes. Mathematically, it's the first derivative of position with respect to time. It contains magnitude, how fast, and a sign indicating direction. Moving against the chosen positive direction means a negative velocity. A negative velocity is not a deficit of speed. It is simply motion in the negative direction of our chosen coordinate system. That brings us to acceleration. Acceleration is strictly the rate at which velocity changes. It is not the rate of change of speed. This chart builds the mathematical hierarchy of kinematics. At the top is position. We differentiate once to find velocity, and again to find acceleration. An operation on the top tier cascades downward, locking in the equations below it. Because acceleration modifies a signed value, velocity, its own sign only tells us which mathematical direction the velocity is shifting along the number line. It does not inherently tell us if the physical object is moving faster. Position tells us where the object is. Velocity tells us how the position is changing. Acceleration tells us how the velocity is changing. To evaluate speeding up or slowing down, we map velocity and acceleration simultaneously on a 2x2 grid. Case 1. Positive velocity and positive acceleration. The object moves forward and speeds up. Case 2. Positive velocity but negative acceleration. The object is moving forward but the velocity is being pulled toward 0. The object slows down. Case 3. Negative velocity with positive acceleration. The object moves backward but the velocity is shifting in the positive direction, back toward 0. It moves backward and slows down. Case 4. Negative velocity and negative acceleration. It moves backward and speeds up. Notice the diagonal symmetry. Matching signs compound to increase absolute value. Opposing signs shrink it toward 0. The physical phenomenon of speeding up or slowing down is determined purely by the relationship between the first and second derivatives. Let's apply this matrix to a physical test case, throwing a ball straight upward. We define the ground as 0 and upward as positive. As the ball rises, governing equations track its state. Gravity ensures acceleration is a constant -32. During the launch phase, the ball's velocity is positive, but its acceleration is negative. Conflicting signs dictate that the ball moves upward but slows down. We pause exactly as the ball reaches its highest altitude. For a single instant, velocity equals 0. This is a cognitive trap. Assuming 0 velocity means 0 acceleration. Notice the acceleration is still -32. If acceleration were 0 at this apex, the ball would freeze in midair indefinitely. Instead, negative acceleration pulls velocity past 0. On the descent, velocity and acceleration are both negative. Matching signs mean the ball speeds up as it falls. A single constant negative acceleration orchestrates this entire physical arc. It slows the ball down, stops it, and speeds it up in reverse. Now we execute a test to prove how malleable these mathematics are. What if we declare that downward is the positive direction? Here is the exact same throw running simultaneously. Left, upward is positive. Right, downward is positive. Physically, they behave identically. But look at the right. Because the ball falls in our new positive direction, its downward velocity is mathematically positive and increasing. Gravity did not reverse its physical pull. The ball hits the ground with the exact same force at the exact same time. The math changed because gravity points down, and we defined down as positive. Therefore, the acceleration due to gravity is now mathematically positive 32. The mathematical signs of velocity and acceleration are not fundamental laws of nature. They are arbitrary artifacts of our chosen coordinate system. This is why analyzing a single derivative in isolation creates paradoxes, like a vehicle braking violently while experiencing positive acceleration. As this graphic shows, positive and negative only have meaning when compared against each other within a specific coordinate framework. Speed is always the absolute value of velocity. If the signs match, speed increases. If they conflict, speed decreases. The equations of motion are merely a language we use to describe reality. They are not the reality itself. True kinematic mastery does not come from memorizing these equations. It comes from reading the relationship between the first and second derivatives to decode the complete physical story.